the temperature scale. To it's going to be expansion of materials. Due to heat flow. 3. Is going to be specific heat capacity and heat of fusion and vaporization. And then 4, radiation of heat from an object. 5, conduction of heat through solids. So it's a pretty big chapter, a lot of materials in there. Temperature scale, expansion of materials due to heat flow, specific heat capacity, heat of fusion and vaporization. And then we could put here calorimetry. Radiation of heat, and then conduction of heat. Okay, so the temperature scale is a pretty easy topic. You're just learning the conversion between Fahrenheit and Celsius, Kelvin. So Kelvin is going to be Celsius plus 273.15. So the Kelvin is the absolute temperature scale, and absolute 0 refers to the coldest possible temperature that you can achieve, and at absolute 0 Kelvin, all motion of molecules stops. So if Kelvin equals 0, then the corresponding Celsius is negative 273.15 Celsius. So this is absolute 0.
Is that a 0.15?
Yeah. And of course, at 0 Celsius, right? So if the Celsius is 0, what would the Kelvin be? And the corresponding Kelvin will be 273.15. And then we say that's the freezing point or melting point of water. At standard temperature and pressure, right? At atmospheric pressure. So at STP. Standard temperature and pressure, the melting point or freezing point of water is 0 Celsius. So the Celsius scale is kind of a random scale because Celsius is 0 corresponds to the freezing point of water only on the Earth, right? And only at sea level, you see. So that's why it's not a scientific scale, because it only is on Earth, plus you have to be at sea level for it to melt at 0. If you go up to a higher pressure, what's going to happen? Up in the mountains, is water going to melt or freeze higher than 0 or lower? So think about it this way: if solid, you're going from a solid to a liquid, right? So I'll try to visualize this. So imagine that you have a cube of ice and it's 0 Celsius.
Yeah.
So then as you're heating the ice from -4 to -3 to -2 to -1, right? What's happening to the motion? The molecules are beginning to vibrate more and more, right? Vibrate more and more and more. So 0 Celsius happens to be that temperature at which, when those molecules are vibrating, then something is happening to break that bond, I guess, so that it's turning from what we call a solid to a liquid, where it just kind of flows more, right? So, but that only occurs at pressure of 1 atmosphere, which is how many pascals? Remember from Physics 101? 101.3 kilopascals. That's the pressure at atmosphere, right? Sea level, 101.3 kilopascals. So now if I increase the pressure, there's more pressure on this, right? Harder pressure. Is that gonna make it harder for it to melt or easier?
Harder.
Harder.
Yeah, it seems like when you increase the pressure, right? So those molecules are starting to vibrate more. For them to change to a liquid and so be able to flow, but there's more pressure on them. So I'm kind of thinking just from a very childish, from a kiddish point of view, right? The pressure on them, doesn't allow them to do the flowing action, So it would kind of make sense from that point of view. As you increase the pressure, the melting point goes up. As pressure goes up, T melting goes up. So that means it becomes harder to melt the ice. Well, opposite of that is freezing. If whatever is true for melting should be the opposite, should be the same true for freezing. So now, if you're trying to freeze liquid water by cooling it, this time it should be easier. You see, you're going backwards. So you're going from, let's say, 6 Celsius to 5 to 4 to 3. Let's say the melting point is now 1 Celsius. So 1, now it freezes when the pressure is higher. Okay, so if the melting point went up, it became harder to melt the ice, but now by virtue of that became easier to freeze the liquid water when the pressure went up. Okay? Because melting has to be the same as freezing. They can't be different temperatures. It can't be like this goes up and the freezing goes down, Now, so therefore, whatever arguments we have for this should also hold for the boiling of water and the condensation of steam from gas to liquid. That's called condensation, right? And then boiling is from liquid water to gaseous water. So as pressure goes up, T boiling goes up. So now becomes harder to boil water, right? But easier to condense steam. Right? So therefore, as pressure goes up, T melting goes up, it becomes harder to melt water, but easier to what? Freeze, I should say, melt ice, right? Becomes harder to melt the ice, but easier to freeze water. Let's see if my kiddish logic holds. For most substances, increasing the pressure when a system is in equilibrium between liquid and solid will increase the phase transition temperature. Yay! Be excited. But since water fills a smaller volume when it's liquid rather than solid, it will go to a lower melting point. What the? Oh. So hold on. But since water fills a smaller volume when it is a liquid rather than a solid, you will go to a lower melting point, allowing more solid to become liquid. So increasing the pressure. Oh, you will be allowing more solid to become liquid. For water, my logic did not hold. Because water is one of the only substances, well, that's what we're gonna learn when we go to the expansion of materials, right? When heated, most materials increase in volume, except for water, okay? Water, when you go from solid to liquid, it actually decreases in volume. And when you go from 0 to 4 Celsius, water also decreases in volume. So it behaves different, okay? So for water, this does not hold. So being kiddish sometimes doesn't always work. For water, this is not true. Now, how about for the boiling one? That might be true though. For freezing, it doesn't work. What happens to melting point of, I should say, boiling point of water when pressure increases? At higher elevations where the atmospheric pressure is much lower, the boiling point is also lower. The boiling point increases with increasing pressure up to the critical point, where the gas and liquid properties become identical. Okay, so the boiling point increases. So does that hold true for the boiling point? This one, when the boiling point increases, the boiling point increases with increased pressure. Boiling point, because it becomes harder. Yeah, this part is true. This part is true. Really weird, huh? This part is not true for water. So I should just say this one. For water, this is not true. Only the freezing argument is not true. The other one, it is true. So if I take an ice cube and I press pressure on it, what should happen? Okay, so if you're adding pressure, what should happen? The melting point should go down. That means the ice cube will melt in my hands. Well, I think that's melting for two reasons, because my hand is touching it, so heat is flowing from my hand to the ice cube. So just even if I didn't press it, it's in the air, my hand is warm, it's touching it, so ice is of course gonna melt. We're not surprised about that. But increasing the pressure, if it was true that increasing the pressure would increase the temperature of the ice, that might fight against the fact that heat is flowing from my hand to the ice, so the ice might not melt. It might kind of keep it equilibrium. But because what's happening is for water, this is not true. Increasing pressure lowers the melting point. When it lowers the melting point, what happens? The ice cube that's at 0 begins to turn to water. You see? By increasing the pressure, the ice cube, because the melting point is lower, the ice cube turns into water more than it would have if this wasn't true. If this was true, maybe less ice would have melted. But because it's true, more ice will melt. We should do an experiment. Press water, an ice cube of water, and then press an ice cube of some other substance, like freeze something else. Take that and press it. What else? Like aluminum? No, but aluminum is not gonna melt. Something that is like has a melting point close to, what other substance is there that we can experiment with that melts around water? I can't think of now, but if you did it, you would see that for that substance, when you squeeze it, it's not melting, right? So let's just say aluminum. Let's say you increase the temperature of aluminum to its melting point, a solid aluminum piece. Increase it to its melting point, but now exert pressure on it. You would find that the aluminum will not melt as much as the water, right, by squeezing it. But the water, the ice melts. But at the boiling, it is still holds true. Okay, so all that to say that going back to the scale, that the 0 Celsius is kind of a random scale. Okay, so now the other important scale is the Celsius 100, which goes to Kelvin 373.15. And so this is the boiling point or condensation point of steam at standard temperature and pressure. Okay. So now that's Kelvin 373. So if we want to know ordinary regular room temperature, we usually call like 25 Celsius room temperature. To make it simple, what we could do is we can say 27 Celsius to make it even. And then we can say that's gonna be our average room temperature. So then if we add 27 to this, we get Kelvin of 300. So that's gonna be our room temperature. When we say something is 300 Kelvin, that's kind of like as if it is at room temperature. That's going to be 27 Celsius. The human body is 37 Celsius. So human temperature. So that means we are about 10 Celsius warmer than the room temperature usually. And we can contain our temperature by regulating the energy flow into our body so that we kind of maintain homeostasis and we maintain our temperature about 10 degrees hotter than room. So that would correspond to a temperature of 310 Kelvin. So that's 310 Kelvin would be our human body temperature. You see. Okay, now let's do the conversion to Fahrenheit. The Fahrenheit scale is going to be 9/5 Celsius plus 32. There's probably a whole history of the Fahrenheit scale, how it came about and stuff. I believe it's a person named Fahrenheit, and probably German. So 0 Celsius would correspond to Fahrenheit of 32. 100 Celsius would correspond to, this is because I already know it in my mind, that's 212 Fahrenheit. So what happens is that a unit increase in Fahrenheit is smaller than a unit increase in Celsius. So if I take the derivative of this, I have dF is equal to 9/5 dC. So if dC is 1 Celsius, then dF is 9/5 Fahrenheit, which is 1.8. So if the temperature of something increases or decreases by 1 Celsius, its corresponding temperature in Fahrenheit increases by 1 or decreases by, increases by 1.8 or decreases by 1.8, you see? So that means it takes about twice more Fahrenheit change for it for it to equal to 1 Celsius change. That's why the Fahrenheit goes from 32 to 212, which is a difference of what? 180. When the Celsius goes from 0 to 100, this one goes to a difference of 180. So the difference is a lot more. And the ratio of 180 to 100 is 1.8. You see. So therefore, Celsius of negative 273 for the 0 Kelvin is going to be what? Negative 273.15 is going to equal what Fahrenheit? So then we would have to multiply that by 1.8. And of course you can check with me, 1.8 plus 32. So negative 459.67. So notice the Celsius went from 0 to negative 273. Fahrenheit went from 32 all the way down to negative 459. So again, the change in Fahrenheit is 1.8 greater than the change in Celsius, right? So then if we want to say what's the regular room temperature, if we call the Celsius 27 Celsius, Fahrenheit would be what? 27 times, you just do 1.8 plus 32. So that's 80.6. That's kind of on the warmer side, 27 Celsius. So that's why room temperature, more comfortable room temperature is probably like 20, 21, 22, something like that. So that's more like a 75 Fahrenheit, something like that. So then the body temperature, Celsius, is 37. What is that in Fahrenheit? Anyone know off the top of their head? When you go to the doctor, what's the regular temperature? I believe it's 98.6. Or is it 7? Yeah, 98.6. So if you're running a fever of 1 Celsius, what's your Fahrenheit? Do I have to do the formula all over again? No, I can use this rule of 1 to 1.8, right? So that would be you running a fever of 1 Celsius would be you running a fever of 1.8, which would be what? 100.4. You just keep adding 1.8. If you're running a fever of 39, 1.8 to 100 is going to be 102.2. So that's actually a lot. 39 in every other country, you're rushing to the doctors. You're only up 2 Celsius. It's really bad fever. But 2 Fahrenheit in this country is not as much. Okay, you may be taking some antibiotic because 2 Celsius is like almost 4 Fahrenheit, you see. So that's why the Celsius scale is a bigger scale, okay? So we can ask now questions such as this. Is there a temperature where the Celsius and the Fahrenheit are equal? So what temperature is there where temperature in Fahrenheit equals temperature in Celsius? And there might not be any answer like that. It might not be true, but we can just still ask it. So then we would just put here, to solve something like that, we just put here F is 9/5 C, then just put, either change this to F, the C to F, or change the F to C, you know. So F equals 9/5 C plus 32. Then here, let's just say, change this to C. And then solve for C. So then C would be, let's see, 5, negative 4, 5, C is 32. Celsius would be 32 times negative 5/4, negative 40. So that means negative 40 Celsius. Let's try to see if that works. If I put that back into my equation, if I did the answer correct, and I put negative 40 here, I should get back Fahrenheit is 40, negative 40. So F is 9/5 negative 40 plus 32, and then 9/5, that's gonna be 8, 9, negative 72 plus 32, negative 40. That's odd, huh? So if you cool your temperature, so 0 Celsius is 32 Fahrenheit. If you go cooler than 0, the Fahrenheit is going down quicker, you see? So it's like the 0 Celsius is 32 Fahrenheit. If you cool this, this is going down, this is going down, you see? And then when you get to negative 40, now the Fahrenheit is now matching the Celsius. That's kind of weird. Now if you go below negative 40 Celsius, then the Fahrenheit is going lower, you see? So the Fahrenheit is changing more, you see? So 0 Celsius and the Fahrenheit 32 is like here, you see? Then you go down, the negative 40 is here. Then if you go down more, the Fahrenheit keeps going down further until the Fahrenheit is negative 459. Well, you could have, so if you're watching the news and you say, oh, some country is negative 40, there are like some, you know, places in Alaska or some Canada or Russia where it's very, very cold, negative 40 Celsius. Then you can kind of say, no, negative 40 Celsius is the same thing as negative 40 Fahrenheit here. You can kind of compare them. That's the base. That's kind of like the base of your start. You could have kind of wild fun with these kind of questions, just scale questions. You could say, is there a temperature where temperature in Fahrenheit equals temperature in Kelvin? And what is that temperature? So you see, right now we don't know really, oh, okay, wait, the Kelvin temperature has to be the same as the Fahrenheit. Is there something like that? So then you say temperature in Fahrenheit is 9/5 Celsius plus 32. Temperature in Kelvin, Celsius plus 273.15. There probably is. Then you can just go 9/5 minus C, 4, and then 32 subtract.
251.
And C equals 251.15 times 5/4.
241.
Huh?
Sorry, it's 241.
Oh, 241.
Yeah.
Okay. And then times 5/4. .4. Oh, but you haven't answered the question. You found the Celsius temperature at which the Fahrenheit and the Kelvin are equal. So now what is that Fahrenheit and Kelvin? So now you take the Celsius answer, then you change it to the Kelvin, which is easy. 301 plus 0.4 plus 273. So then the Fahrenheit would be what? 301 plus 273, so then it's going to be what? 574.55. 574.55 Fahrenheit. Then the Kelvin, you know, would also be 574. Oh no, sorry, I did the Kelvin. That was the Kelvin. I did this on Kelvin. So the Fahrenheit, the Fahrenheit would also be the same. 574.555. So now what's gonna happen as I go above that temperature? Is the Fahrenheit gonna be above? Let's say if I go to 575 Fahrenheit. One unit of Fahrenheit is equal to how many units of Kelvin? Well, what we could do is, what's the dk dc? If I take the derivative of this, Kelvin and Celsius, dk is dc. So 1 degree change of Celsius is 1 degree change of Kelvin. Let's see. So that means the same rule holds true. If the Kelvin goes up by 1, the Fahrenheit is going up by 1.8. Let's see. So that means if I go to 575.55 Kelvin, the Fahrenheit goes up by 1.8, which becomes 570, let's see here, 576 Fahrenheit. That means the temperature at which the Fahrenheit and the Kelvin are equal is 574, like this. After that, the Fahrenheit starts going more up than the Kelvin. Let's see. So 575 Kelvin is the same thing as 576 Fahrenheit. Now, if you really want to have fun with these kind of questions, ask just purely random ones that have no intrinsic application value. Something like, what temperature is there for which, well, let's word it first, for which the square what temperature is there for which the square root of the Fahrenheit is equal to the log of Kelvin? Just random, just for the sake of asking it. Okay, so how would you set up things like that? So then I could just do it similar to how I have it here, right? The square root of the Fahrenheit is equal to the log of the Kelvin. What I could do is, so that I'm not only just doing it in terms of Celsius, I could get a formula for the conversion between straight from Kelvin to Fahrenheit, so that I'm not necessarily going to Celsius. I could say Kelvin is Celsius plus 273.15. Fahrenheit is 9/5 Celsius plus 32. I could say Celsius equals Kelvin minus 273.15. Put it here. Fahrenheit is 9/5 Kelvin minus 273.15 plus 32. So now I have a straight up conversion between Fahrenheit and Kelvin. 9/5 Kelvin, and then distribute this in. Negative 459.67. Oh, that makes sense because when you're 0 Kelvin, remember the absolute zero, you are negative 459 Fahrenheit. Yeah, that makes sense. So that's a straight up conversion between Fahrenheit and Kelvin. Now, if the question asks something like that, we have temperature, square root of the Fahrenheit temperature is log of Kelvin, so square root of 9/5 Kelvin minus and then put that in solver in your TI. Remember last semester we were using on the internet, we were kept using this site. Let's see where was that. Region calculator. That one. So on your TI, you would put this into solver. So square root of that it? Yeah? Maybe there's no solution. Log of base. Is there an answer? Are you guys getting one? This one's not giving me one. That one's those kind of problems are hard to solve. I mean, you square both sides, there's no way. I mean, nothing. It's more graphical you have to solve. Do you have anything on yours?
258.61.
You got it?
Yeah.
258.61. I'm surprised why you didn't give us.
But
Usually would have given us.
estimation.
You did estimation? 258.61. Mine is out of battery because the winter session was long. So get those batteries juiced up again. Well, you could always try it. Take 258, take log of it,
Yeah.
right? So if I give this to you on the test, which probably I will, right? You could always then try it. Just take the log of that number, take the square root of that number. If you get it.
Professor, where'd you find those solvers for the TI?
The TI, it depends which TI you have.
I have an 83.
Yeah, then you would go to math, you would scroll down to the bottom where it says solver. Do you have it with you? Yeah, I'll show you once you have it. We could do it together, I'll show you. So depending on which TI you'll have, learn the solver option for that. I think that's all I'm gonna say in terms of the, you have a good feeling for the scales now, the Celsius, the Fahrenheit, the main temperatures for them. Okay, now let's go to expansion of materials. Length expansion, volume expansion. So, expansion of materials is an important topic in many different areas. This one shows you a simple example of when you're building a bridge that you want to put expansion joints. Expansion joint in a road bridge used to avoid damage from thermal expansion. So pretty much a lot of things we have, we kind of already naturally account for that expansion. You know, if we don't, we get damage in property. Even simple things like the tile on the floor, if you notice that there's a little gap between the tile where we put grout, and we allow for there is a little bit, even though it's very, very thin and almost unnoticeable, you have to have that grout. So the grout is this little sticky plastic thing that can be contracted and expanded. Depending on if the tile expands, the grout makes up for that by contracting slightly. When you're making tile in your restrooms, your kitchen, everywhere like that on the ground, you have to have that area. For this expansion, you have to have places in the road, and even probably buildings too, inside of buildings. You have to have places where the material can expand. The other area where expansion is also useful and known is like the old style thermometers. They're not as much in use now, but they were based on the expansion of material, these ones. They're very, very accurate. But when you go to the doctor's office, they don't use them that much anymore because they don't want to put a mercury tube in your mouth. You know, this is kind of how we grew up, right? You have a mercury tube, and so it's kind of calibrated already so that at room temperature, it's gonna show, and then whoever made this made it so that they put a certain amount of mercury, and then they made the scale so that it should show the room temperature. And then when you put it in your mouth, it should go up slightly. So right now, if it says, let's say 20, 22, 23, it's gonna go up slightly to 37. Why? Because inside your mouth is gonna be warmer, and it's gonna cause the liquid mercury to expand, right? Because mercury is a liquid at room temperature. It's kind of an interesting solid. So the liquid is gonna expand volumetrically. That's called volumetric expansion of a solid. So it expands inside of the tube until it reaches 37, you see. So that's based on volumetric expansion of a liquid. The other tool that we have that's very commonly used is, or even these things, there's dials. It's probably based on that too. The other one that I was gonna show you is the bimetallic strip. They're usually put in the thermostats to control the temperature of an AC circuit, AC and DC. So bimetallic strip is a temperature-sensitive electrical contact used in some thermostats consisting of two bands of different metals joined face-to-face along their lengths. So you take two metals, fuse them together, and they expand at different rates. So since they're fused, if the bottom one expands more, it's gonna push on the top one, and it's gonna curl like that, right? And if it cools, it's gonna go back like that. So those bimetallic strips use that expansion of materials. When heated, the metals expand at different rates, causing the strip to bend, and then, how are they made? Room temperature. So see, when you're heating it, you have two materials here, then it's bending. You see here, brass and steel, for example. When heating, it's bending like this. Just from the picture, which one has a bigger expansion material coefficient? Brass, right? It's expanding more. When cooling, it's going the other way. This is contracting, you see, more than this one. So therefore it's bending this way. So in both scenarios, brass is the one that has a bigger coefficient of expansion, you see? And then in the bimetallic strip, you're putting it here, like this. So it's the coil, when it's expanding, it's going like this, and then triggering the balance. You can look there. Oh yeah, you see? I think this picture is a nicer one. See, here's the bimetallic strip, here's the contact. So basically, if it's heated, the bimetallic strip is gonna go, let's say like this, touch the contact. Once it touches the contact, let's say the heater turns on. And see, if it's heated, no. If it's heated, if it's too hot, oh no, the opposite. If it's heated, it goes like this and touches the contact, that means it's too hot in the room. The AC turns on, you see? And then if it's too cold, maybe it goes down, and maybe there's another contact at the bottom. If it's too cold, it goes down, and then let's say there's one contact at the bottom. It touches that, the heater turns on. So you can have it set both. That's why when you're deciding to do heating mode or cooling mode, you're probably engaging this one, and then there's another one at the bottom, right? So if you do heating mode, then you're engaging the other one. When it's too cold, this is going like this, touching this one, and then the heater is turning on. You can see. So amazing. That's one of the good uses of this expansion of materials. Okay, so the formal definition then is you define a constant known as the coefficient of expansion. This is one-dimensional expansion, 1 over L dL dt. So it's actually a derivative concept. Linear coefficient of expansion. This is linear area and volume expansion. So alpha L is 1 over L dL dt. So how much length it expands by how much temperature is required to expand it. So the bigger the alpha, this is called the coefficient of linear expansion. Coefficient of linear expansion. So the bigger the alpha, does it mean it expands more or less? Right? So that means if for example, if the temperature increases 1 Celsius, right? So that for a given temperature change, the bigger the alpha, the more the delta L is. So when you're defining some concept, some constant, you gotta look at the meaning of that constant and what does it mean if that constant is big or small. That to me is very important, right? The meaning of that concept, the units that thing is measured in, plus what does it mean for that thing to be big or small? How does it affect? So this is think of it as this is the definition. And so it's not like a formula. This is how we're defining the alpha. So what does it mean for it to be big? That means for a given temperature change, the length of the object expands more, right? So that means delta L, if delta L is big, alpha is big. Or actually it should be the other way around. If alpha is big, delta L is big. So that means The bigger the alpha, the more it reacts to changes in temperature, and the more that element increases its size, right? So the bigger the alpha, the more that substance expands and contracts. Of course, if it expands when heated, it would mean that it contracts when it's cool. You can see. Now, most of the time you see this not written as a derivative. Why? Because for most substances, the alpha is not temperature dependent very strongly. It's constant, right? So for most substances, alpha L is more or less constant. So when that's the case, what would happen? I can take this dt over to the other side. I can say, without even taking it to the other side, I can say alpha L is approximately equal to 1 over L delta L over delta T, right? So when this thing is constant, that means the rate of change, the instantaneous rate of change of L with respect to T is the same thing as the change over a big length over dt. So then a lot of times this equation is written like this. Delta L is equal to alpha L, L initial, delta T. You see, that's what they're doing there, here. It's saying where L is a particular length measurement as dl dt is the rate of change of that linear dimension. The change in the linear dimension can be estimated to be delta L over L, alpha L, delta T. This estimation works well as long as the linear expansion coefficient does not change much over the change in temperature, right? If the alpha L is more or less constant, then you can change it to a delta. So then, and the fractional change in length is small, okay? So then a lot of times it's just written like this. And then now we can kind of look at the alpha of different materials. Saying this is what happens when you don't take into account expansion of materials. Before, when we made train tracks and we weren't making it to exact specifications and we weren't putting gaps, they would bend like that. That's quite severe, huh? Thermal expansion of a long continuous section of a rail track is the driving force for rail buckling. This phenomenon resulted in 190 train derailments between 1998 to 2002. That's actually recent, I'm surprised, in the US alone. You would think by 1998 we got our acts together. That's really, really weird. Oh my gosh. That's quite severe, right? Like that. Okay, so these are different expansion of materials. Aluminum 23.1 times 10 to the minus 6. So what is the units, by the way, of the alpha? So this is delta L is meters, this is meters. So then it's just gonna be 1 over dt, which is Celsius, rate of change of Celsius. But it could be a rate of change of Kelvin because dt in Celsius is the same as dt in Kelvin, right? Because remember that we saw the equation. So dk is dc. So 1 unit change of Celsius is a unit change in Kelvin. So that means the units of the alpha can be 1 over Kelvin or 1 over Celsius. Usually most people put 1 over Celsius, but here they put 1 over Kelvin. So aluminum is going to be 23.1 times 10 to the minus 6, 1 over Celsius. Brass is 19, So of course that means if you put aluminum and brass together, the aluminum would expand more, and then whichever one is that, it will bend it, right, towards the direction of the brass. So brass is 19. And then carbon 10, concrete 12, copper 17, diamond 1, ethanol 250, gasoline. It's weird that they would put gasoline linear expansion. Because usually for solids we have linear expansion, but for liquids we don't have such a thing as linear expansion. Liquids are all volume expansion. So now notice what happens. Volume expansion is generally what? 3 times the linear, you see? So this times 3 gives you this times 3 gives you that. So we know this is a pattern, but for gasoline, yeah, they did it the same way. But I don't know why they have a linear for gasoline. Carbon doesn't expand much, diamond doesn't expand much because it's very hard material. Ice, 51. You can see all the materials that are there. Platinum, PVC, fused quartz, rubber, sapphire, silicon, silver, stainless steel. Stainless steel has a range of values. Titanium. Water is 69 and 207. So why this 3 rule? What's happening here? Well, in order to do that, let's see what would happen to, let's go up here. They do it kind of like they're saying what happens if it's a 2-dimensional expansion and if it's 3-dimensional expansion. You see where they're getting the 3? So the idea of that is, in other words, the length is expanding linearly proportional to L, and then this constant alpha. Of course, nothing is particularly just 1-dimensional. We live in a 3-dimensional world, right? So, but 1-dimensional object we take as those objects where one of the dimensions is quite longer than any of the other dimensions. So, such as a rod, let's say, like this, like those train tracks or something. So it could have a width and a height and a width. And if those are insignificant compared to the length, we can say pretty much the expansion is happening only along the length because it's dominating the expansion of the other sides, right? Why? Because the equation is saying delta L is, the change in length is proportional to the original length. So of course, if the original length is much longer than the length, the height and the width, its change in length is gonna dominate over the other ones, and we could ignore the other ones, right? But then what happens when one of the dimensions is also kind of big, height and length, and now only the third dimension is negligible, right? So now the length is gonna expand, the height is gonna expand kind of appreciably, but now the width is negligible. So, right? So then what are we gonna say? The length of this expands, delta L is alpha L initial delta T, and the height expands, alpha H initial delta T. So now what's the new area of this shape? Right, so now how much does the area increase? We say A final is equal to what? L initial plus delta L times H initial plus delta H. In other words, if I want to know the final area of this face, right? I don't need to worry about that top face because it's not expanding appreciably. So then I could take the final length time multiply it by the final height. So now I'm multiplying here L initial H initial plus L initial delta H plus H initial delta L plus delta L delta H. Right? And then now I'm going to have a final L initial H initial is the initial area. Right? And now L initial delta H, well then delta H is going to be alpha H initial delta T. Then H initial delta T, delta L is going to be alpha L initial delta T plus delta L delta H. So then you're going to have alpha L initial delta T, alpha H initial delta T. Okay, so then you're going to have your A final is A initial plus, well, L initial H initial is the initial area. And then alpha A H initial L initial also initial area. And then alpha squared. And then L initial H initial area delta T squared. And now what do you get? A final minus A initial is delta A is equal to, I can add these two, 2 alpha A initial delta T plus alpha squared A initial delta T squared. You see where the 2 alpha is coming from? That means we can define a new constant, call it the area expansion coefficient, alpha A, which is twice the length expansion. You see? So what's happening to that second portion, the alpha squared A delta T squared? What's happening to that one? Well, they're kind of ignoring that. Similarly, the area thermal expansion coefficient is 2 times the linear coefficient. Well, for most materials, alpha was what order of power? Remember the power of the 10? Where was it?
-6.
They don't expand a lot, right? 10 to the minus 6. So then what happens? If I take alpha squared, I'm going to get 10 to the minus 6 times 10 to the minus 6. 10 to the minus 12. Well, how much am I going to increase the temperature so that the 10 to the minus 12, I multiply it with some number that makes it noticeable? So that means this term is not noticeable compared to this term. This is 10 to the minus 6. This is 10 to the minus 12, right? Boom, boom, not noticeable. Even this is not noticeable, but at least it dominates over that. So not noticeable. So this is the equation that we use when the 2 dimensions of the object are big, but the third is not. That means the area of the object increases by this equation. 2 alpha A initial delta T. The area of that object changes based on its original area and the temperature, but twice the alpha. So can I use this equation other than just if it's a rectangle? What if the object is a circle? And it has an initial radius of r. what's gonna be the final radius of the object when I heat it by a certain temperature? Can I increase this? I should be able to use this equation, right?
Yeah.
I could say delta A is gonna be 2 alpha, what's the initial area? Pi r initial squared, right? And then delta T and so then delta A is gonna be 2 alpha pi r initial squared delta T. But then remember, delta A is A final minus A initial. A final minus A initial. But then what's A initial? Yeah, A initial is pi r squared, right? So then A final is gonna be pi r initial squared plus 2 alpha pi r initial squared delta T. You see? So the delta A is the change in the area, is proportional to the twice the alpha times the original area times delta T. But then I add that to the original area is pi r initial squared. That's gonna give me the final area, so we could say the A final is pi r initial squared 1 plus 2 alpha delta T. Right? Now if I want to know what the final radius is, I could say A final is pi r final squared. Then pi cancel the pi, and then our final is going to be square root of this. It's kind of a weird formula came out. So the radius is going to increase as a square root function. 1 plus 2 alpha square root of the delta T. So you could take this equation and apply it to shapes that are non-rectangular. Right? It could be circles, it could be anything. Equilateral triangle. Oh, good test question. Equilateral triangle. Initial side S, then you increase temperature. What's the final side? Don't tell the teacher that I told you that he's about to put that on the test. Okay, good time to take our break. Around 12:40, that's like when I want to